So I just want to say welcome, everybody. My name is Alicia, and I'm the Executive Director of the Salt Ponds Coalition. For the past 3 years, the SBC has been partners in a grant funded by the EPA with the Town of Charlestown, the University of Rhode Island, and Save the Bay. The goal of this project was to implement various methods aimed at reducing nutrients in the groundwater and surface waters in the Charlestown area, including the salt ponds, which included upgrading substandard or failing septic systems, optimizing the functionality of existing denitrification systems, and installing rain gardens. SBC was happy to provide water quality testing for this grant, as well as doing a lot of the educational and outreach materials development, like this seminar tonight. We have 3 presenters tonight. One thing that I'm going to ask is if you have any questions, just hold your questions until all 3 presenters have spoken, and we'll talk a little bit more about that when we get to the end of the program. So now I'm going to introduce who our presenters are. First, we have Matt Dowling. He is the on-site wastewater manager for the Town of Charlestown. We have Bianca Ross, who's a postdoctoral fellow at the Environmental Protection Agency, and Alyssa Cox, who is the director of the on-site wastewater training program at the University of Rhode Island. So once again, for anybody who's just joined us, if you don't mind just muting yourself before we start the presentation, and I am going to hand it over to Matt to start.
Hi, everybody. Thank you for coming. I really appreciate it. This is exciting. As Alicia said, I'm Matt Dowling. I'm with the Town of Charlestown's on-site wastewater management program as my full-time job. And part of my job over the past 4 or so years has been to manage portions of this grant that we got through the EPA. It was a 4-year grant. We got an extension because of some COVID issues that we had some difficulty getting some of the projects done this year. 2020 has been a little tough for that, but I'm going to talk about a small portion of this, a small portion of the larger grant, which was managed by my office, which included the upgrade of 15 substandard septic systems within a specific watershed of the coastal zone in Charlestown. We focused our work specifically in the Green Hill Pond and Eastern Ninigret Pond watersheds, specifically because that's the most densely developed area in Charlestown, and it abuts the most nutrient and bacteria impacted watersheds in town. So I'm going to share my screen with my presentation here, and we're going to run through this so you can learn about exactly what I did as part of as my part of the grant. Alicia, can everybody see this and can everybody hear me?
Yep, we can see it.
Okay, so just a general overview for this portion of the project. We know that groundwater in the coastal zone of Charlestown is impacted by nitrogen. And we also know that Charlestown is kind of unique as a coastal community. We rely solely on groundwater for drinking water purposes in town, and we only have septic systems to manage our wastewater. Charlestown is one of only 2 communities in the whole state of Rhode Island that one of the only 2 coastal communities in the whole state of Rhode Island that actually fits these criteria. The other is Little Compton. They have no, like us, they have no municipal sewer collection system, and they have no real public, large-scale public water. But Charlestown's a little bit different because we're much more densely developed than Little Compton is. We have areas that are developed on 1/10 of an acre lots down in the Charlestown Beach Road area and Quanticook to some degree on the coast. So we also know that 80% of groundwater nitrogen in the densely developed areas of Charlestown actually originates from septic systems. And we know that from some modeling that was done by the URI Cooperative Extension back in 2014. Nitrogen concentrations, we've documented that they are above drinking water standards in some areas, which poses health risks and negatively affects the water quality in coastal ponds, as that nutrient-laden groundwater makes its way out to our ponds and creates nutrient overloads and algal blooms and periodically hypoxic conditions in some areas of the salt ponds. So like I said, we know that there's a significant relationship between the density of septic systems and groundwater quality. And we know this because we, let's see here. Standing by. Okay. We know that there's a relationship between groundwater quality and density of septic systems because over the past few years, we looked at over 240 private drinking water wells, and we sampled them for a series of geochemical parameters, including nitrate and total nitrogen. And what we found was, looking at these 239 wells, we found that there is a linear relationship between the density of septic systems and the concentrations of nitrate in groundwater. So we took that density relationship, and we actually created a GIS map using that relationship of the coastal zone of Charlestown that predicts groundwater nitrogen concentrations based on this relationship and the density of development. It enabled the town to look at potential zones of hotspot nitrogen contamination, and those overlap quite well with our densest developed zones. So nitrogen threat from septic systems, that can be mitigated with nitrogen reducing technology. Every substandard septic system, substandard and conventional septic system that's replaced with a nitrogen reducing septic system can reduce the total nitrogen load to the watershed by at least half. And in a lot of cases, it's actually more than that. So, knowing all this, we developed a program to upgrade 15 substandard septic systems in the most critically sensitive and overdeveloped salt ponds watersheds in Charlestown. That was started in 2018. We used $270,000 of EPA SNEP, that's the Southern New England program, focuses on coastal restoration. We used $270,000 of that grant funding was allocated to provide 75% reimbursement to homeowners who agreed to enter into a program to upgrade their substandard septic system to nitrogen reducing technology. This graphic here is actually one of our some drone footage of one of our installations that we did under this grant, and you can see the septic system being installed here. There's erosion and sedimentation control. This was a substandard failing septic system that was actually discharging wastewater into a coastal wetland that's contiguous with Green Hill Pond. So when we excavated to put this system in, we actually found the drain field was off the property into the coastal wetland from the substandard system. A lot of these systems were installed before there were any septic system regulations. Prior to 1968, there was no oversight for septic system installations, and a lot of our older dwelling units in that watershed were actually constructed before that time. So a lot of them have substandard septic systems that were installed.
The missing part is gathering the research. The hard part is reading.
So moving along. So how do we identify the sites? So we knew that, looking at our GIS analysis, we knew where the densest zones were. We knew where the hot spots of nitrogen were likely to be in groundwater based on our well sampling. And we also knew where we know where all of our substandard systems are as part of the town's inspection protocol. So the town of Charlestown retains a comprehensive septic system tracking database. It has every septic system in town, what type it is, what its management schedule is, and where it's located on the property, how old it is, what the average use is to some degree. So we were interested in substandard septic systems. So what is a substandard septic system? We classify those at the town as being anything that's substandard is lumped into a group that could consist of cesspools. There's not many cesspools remaining in Charlestown. We had a very successful cesspool phase-out program that we implemented over the last decade. It's pretty much come to a close now, but there still are a few. So cesspools, any failing septic system that could pose an imminent threat to human health or the environment. Septic systems with steel tanks. There's actually quite a few of those in the Charlestown Beach Road area. And any septic tank that's less than 1,000 gallons, it doesn't provide adequate retention time for sufficient treatment of wastewater. And then any septic system that was installed before 1968 that doesn't meet any of those permitting guidelines that I previously spoke of. So the density of the substandard systems, we plotted those out on GIS, and we basically developed this map you see on the right of your screen showing overlapping circles of every substandard system. And it clearly we did this for the whole town, and I only cut out this one section because it was very telling where our highest density of substandard septic systems were located. And this is Allen's Cove here of Green Hill Pond, and this is Eastern Ingrate Pond here. This is Arches Cove, Tuckwatton Cove, and here's Fort Neck here. Can you all see my cursor? Alicia, yeah, okay, good. So yeah, right in this area, we have this really high density of substandard septic systems. So obviously substandard septic systems do little to treat bacteria and little to nothing to treat nutrients emanating out into the groundwater. So like I said, we allocated $270,000 to provide 75% reimbursement for property owners to upgrade those types of septic systems. The program is set up to reimburse homeowners up to $18,000 per septic system. There was a cap put at $18,000. We wanted to have property owners have some buy-in, so they're a part of the process. So, we covered a cap of $18,000 or up to 75% of the total cost, up to $18,000. Property owners incurred all other costs. And what we found with, homeowners were really engaged, and that was what we were shooting for. We wanted to have a conversation. We wanted to have a relationship with the property owners. So, my initial analysis based on published loading rates from conventional septic systems and reductions from nitrogen reducing technology, I calculated that if we upgraded these 15 septic systems in this one geographic area, we were likely to reduce the total poundage of nitrogen being outwelled into the groundwater and subsequently out into the salt ponds by up to 150 pounds per year. That was my initial assessment. And that's what I put in the grant proposal that was selected by the EPA. So again, how do we identify the site? So we use that overlay of the density of substandard septic systems, and we also use, like I said, we use the projected groundwater nitrogen concentration maps, and we called out this one particular area that we were really interested in along Allen's Cove and Eastern Ninigret Pond. So in that area, we looked at 174 substandard septic systems were identified using our GIS and our database. We developed an application process and we submitted written correspondence making homeowners known of this grant opportunity. We actually sent that to 233 property owners. We expanded our outreach to just beyond this 174 group of dense systems. So there were a few other substandard septic systems within this watershed that we also reached out to. So out of those 233 letters that we sent out to homeowners, we received 44 responses by the due date, which was a 18% rate of return, which I thought was actually fairly high, all things considered. So once we got all those 44 applications in, we had to figure out a way to identify the sites that would have the most bang for the buck, so to speak. How are we going to identify sites that we're going to maximize the nutrient reduction? So I developed a ranking protocol to identify which sites would sort of rise to the top as far as need goes. So the components that we had the homeowners include on our application was septic system type, the number of bedrooms. Obviously, the higher number of the bedrooms, the more septic flow that is likely to come out of that system. And when DEM designs septic systems, they're actually designed by the number of bedrooms in each system. So larger systems, higher number of bedrooms, more potential nutrient loading. Was the property located within one of our critical nutrient reduction zones, those zones that we carved out from that concentration map? What was the proximity of the property to the inland edge of the coastal feature? Sites that were closer to coastal wetlands or wetlands that were contiguous to the coast, or the coastal bluff, or the edge of the salt pond ranked higher in our analysis. The model predicted groundwater nitrogen concentration. That's from that concentration map that I showed previously. Was the property owner occupied or was it a rental? We granted more points to owner occupied dwelling units. We want, like I said, we wanted to have a relationship with the property owner. We want to work with the property owner. Typically, rental units are also only rented out half the year, and the remainder of the year remain vacant. We wanted to have homeowners that were occupying their property year round. And that's the next point, occupancy. Was it occupied seasonal or was it occupied year round? Obviously, year round occupancy, the system is used, not 3 or 4 months out of the year, but throughout the whole year, thereby theoretically enhancing the potential nutrient load coming out of that dwelling. What was the drinking water source for the property? Was it on a private well or a public water system? Charlestown does have some small community public water systems that service dwellings. There are no community systems in the target area. So every site was utilized a private well for drinking water purposes. And that's another thing about these older septic systems, these substandard septic systems. A lot of them don't meet the setback to the drinking water well, which is 100 feet. Again, quarter acre lots, a tenth of an acre lot. A tenth of an acre lot is there's no way you're going to get your setback to your drinking water well from your septic system. And then we did include some financial assistance, financial points for any applicant who was willing to supply financial information indicating that they did meet the HUD low income guidelines, which is their income was 80% of the median in Charlestown. So we stuffed all that information into a spreadsheet, ranked them, applied points to each one, and the top 15 sites that rose to the top, we selected those for inclusion in this project. So the property owners that were selected, they were required to enter into an agreement with the town, a formal agreement with the town to take part in this program. And by doing so, there was a series of requirements. One of those requirements was, you couldn't sell the house within X amount of time of taking part in the upgrade. You couldn't do any sort of new construction or major home renovation. The septic system replacement couldn't be triggered by adding a level or adding an addition. We wanted to have no additional flow, no new bedrooms. And then finally, one of the other conditions was that property owners had to agree to allow the town and its partners, specifically URI, to grant us access for a period of, I think it was 4 or 5 years, once the system was installed, so we could implement some effluent monitoring to better understand how nitrogen reducing septic systems are managing nutrient reduction. And Bianca is going to talk about some of that coming up next. So once each septic system was installed, the property owners were required to send us all their final invoices, and then we calculated the percent reimbursement up to that $18,000. The interesting thing was we required that each homeowner got 3 bids, and they sent those bids to my office for approval. So what that ended up doing is I ended up getting 3 bids from all the 15 sites. So that gave me a pretty good understanding as to what the typical price for a nitrogen reducing septic system is in Charlestown. So I looked at all the bids, I actually added up all the numbers, and I got the average was right around $27,000. So that's a nice data point that we got out of this. So, that can help property owners better understand, what they're looking at for septic system upgrade costs to nitrogen reducing technology. All upgrades were required to be completed within 1 year of signing the agreement with the town. And my office provided technical support, installation, oversight, and final inspection for each system. So what were the results? Really, I had a ton of positive feedback from the community. I had lots of phone calls. I had lots of interested property owners. It was very well received. So subsequent to my initial analysis of 150 pounds per year, I ended up doing another analysis that looked at specifically every site that was upgraded. What was the actual system type? What was the actual flow? And once I looked at each site that was updated, I ran a calculation and determined that the total net reduction per year of nitrogen wasn't 150 pounds per year. It was actually 357 pounds per year, which I was really surprised at, but very pleased. So, annualized 10-year period, 35,000 pounds of nitrogen removed, kept out of our watersheds. So here's just a graph that just shows, the projected nitrogen loading in the red line over time for 10 years. And here's the nitrogen in pounds. Here's the year, and here is the post upgrade nitrogen loading. So pretty successful. So the results of this were that, it really brought to light that we need to find a funding source to help property owners upgrade older, substandard and conventional septic systems to nitrogen reducing technology in these critically nutrient impacted coastal watersheds. And not only in Charlestown, but all along the salt ponds from westerly to Narragansett. So that's something that we need to keep an eye on. We have to look for grant money. We have to look for programs. We have to think outside the box as to how we can fund future upgrades. Subsequent to the installations, we had all those other applicants, 44 applicants. I had a lot of interest from the others who weren't selected, if there were, asking me if there was going to be additional funding available. I did apply for another SNEP grant to try and get some additional funding, but that proposal wasn't successful. But we do plan on doing more applications in the future. And there was a lot of interest received by others within the watersheds looking for substandard septic system upgrades. This program could be utilized as a model for other jurisdictions facing similar challenges all across the South Shore of Rhode Island. And interestingly enough, this same exact protocol that we used here will be implemented by the town in our partners URI to research a new passive lower cost experimental nitrogen reducing septic system next year. So that's really it. That's the end of my talk here, and here are some references if anybody's interested.
All right, so thank you, Matt. If you want to unshare your screen, I will now hand it over to Bianca Ross.
All right, thank you very much. I am just going to go ahead and share my screen. Get started here. Alrighty, can you all see this? My PowerPoint? Great. Okay. Alrighty. Okay, great. Well, thanks, Matt. That was really interesting. It was an awesome introduction actually into a lot of the sort of more research heavy things in the lab and in the field that I'm going to be speaking about in my presentation today. So again, my name is Bianca Ross. I graduated in May with my PhD from the University of Rhode Island, and I'm currently a postdoc with the US EPA. I'm really excited to be here today and to be speaking with you about my PhD research, where I looked at the treatment performance of these advanced nitrogen removal outs in Charlestown, Rhode Island. So before I begin, I just want to take a moment to thank everybody who has helped me with this research, Matt included. He was a super huge help when it came to choosing our sites and helping us figure out sort of the lay of the land. So that was great. Also, everybody in the Laboratory for Soil Ecology and Microbiology, and all of my funding sources. So just a brief disclaimer. Everything that I'm going to be presenting today, my research was funded by the US EPA. So all of these results are preliminary and they have not yet gone through the EPA's review process. All right, so we're going to start out just with a brief introduction on sort of wastewater and these nitrogen removal outs and why we care, a lot of which Matt has already touched on, which is great. So I will breeze through these because we're already pros, I'm sure. But basically, when it comes to wastewater and nitrogen on our coast, we care because wastewater can, of course, be a major source of nitrogen to these coastal watersheds. Wastewater coming from these on-site wastewater treatment systems are super rich in nitrogen, coming from urine, fecal matter, food, cell material. And again, when you get those large sort of influxes of nutrients, this large boosted numbers of nitrogen, that leads to algal blooms when it makes its way to its coast or to the coast. And as that algae dies off, the oxygen becomes depleted in our waters, and ultimately that leads to eutrophication. So you can see in Greenwich Bay, this was a pretty epic fish kill that happened as a result from eutrophication a few years ago. So eutrophication is very dangerous when it comes to not only environmental health, but also when it comes to public health and just economic health in general, especially when it comes to these coastal towns that are largely dependent on the fish trade, on the shellfish trade. And so that's just sort of one reason why we care so much about the nitrogen that's coming out of these outs. So in order to combat this nitrogen issue, of course, these advanced on-site wastewater treatment systems have been designed in order to remove nitrogen from the wastewater before it enters our water bodies. So before it enters the groundwater and ultimately before it makes its way to the coastal water bodies. So all of these advanced outs, they are basically systems that may look different but have the same focus. They have the same goal. So all of these systems, despite the fact that they may vary in their appearance, in their design scheme, will have different zones to facilitate nitrogen cycle processes. So no matter what system you're dealing with, no matter what technology type, your systems will have an oxic zone, so an area rich in oxygen, and that is where nitrification will happen. So that's sort of the first process in the nitrogen cycle that converts ammonium to nitrate. And the systems will also have an anoxic or hypoxic zone. So that's an area with little to no oxygen. And that's where your denitrification will happen. So denitrification is the final step in the nitrogen removal process. And at that point, nitrogen is effectively removed from wastewater. So nitrate is converted into nitrogen gas, N2, that's the hope. That is a harmless inert gas. Or it could be converted into nitrous oxide, which is actually a sort of a byproduct of this denitrification process. So either way, your nitrogen is being removed and emitted as a gas. But another portion of my research, which I won't be speaking about tonight, actually looked at sort of the nitrous oxide versus the other greenhouse gases produced by these systems in order to check out what's happening there. But essentially, when you are shipping this wastewater through these technologies, again, you're getting that denitrification. That's the hope. By some way, shape, or form, you are releasing the nitrogen into the atmosphere, getting it out of the water. Now, the Rhode Island Department of Environmental Management, Rhode Island DEM, has established a standard for final effluent. So you'll hear me mention that a few times today. Final effluent simply refers to effluent or wastewater that has received its treatment from these outs. It has moved through the treatment process and is about to be shipped out of the system. So DEM states that the total nitrogen concentration in that final effluent needs to be 19 milligram per liter or less. That is the standard for these advanced end removal outs. So here is sort of a general schematic of the flow of this wastewater. This is what we call the nitrogen removal treatment train. The wastewater essentially leaves the house. It enters the septic tank or the area of primary treatment. So in there, gravity forces the separation of the sludge layer. So your solids will sink to the bottom to form your sludge layer. And your lighter materials, your fats, oils, and greases will float to the top to form your scum layer. That clarified wastewater is then what moves on to the secondary treatment portion of the treatment train, or the advanced treatment portion. So that is where we get our nitrogen cycle. For simplicity's sake, I have grouped these oxic and anoxic processes together. As you recall, right, we'll have an oxic zone for nitrification and an anoxic or hypoxic zone for denitrification. So here I've put that all in one tank. However, that's not always necessarily the case. As I mentioned, these technologies vary in their design scheme. You may have them happening in one tank, just a tank that's separated by time, on and off cycles of aeration, or you may have multiple tanks and they sort of recycle throughout those various zones. But no matter what, again, you're going to have the oxic zone for nitrification and the anoxic zone for denitrification. So, and after the advanced treatment, it then moves on to the wastewater moves on to the soil treatment area. So through our advanced treatment, through that nitrogen cycle process, as I mentioned, we have denitrification happening. When it goes to completion, it produces that harmless N2 gas. But if the process does not go to completion, it can produce nitrous oxide, which, as I said, is a potent greenhouse gas. So that is sort of one question that we did consider on our lab, is whether or not we're sort of shipping this nitrogen problem from one medium to another. Are we shipping it from the water to the atmosphere? And again, that's something I won't talk a lot about, or I won't be speaking about tonight, but short version, they weren't doing too bad of a job producing the nitrous oxide. So that was actually really encouraging. So next, I will just sort of discuss the overall how-to of my project, what we looked at. So this study took place between 2017 and 2019. Again, I focused my efforts in Charlestown. We had 50 study sites, and we sampled those sites 4 times a year. Now, the sampling scheme and the timing of those 4 times differed depending on what home occupancy pattern we were looking at. So I say that because in Charlestown, just like in many other coastal towns, you have many residents that live in the town all year round. So they live and they use these systems all year round. But there are also many just seasonal residents, people who only have summer homes there. They're only using these systems in the summer months. So because of that, we wanted to target whether or not that variation in home occupancy pattern is influencing the performance of these systems. So because of that, we did about an even split of year-round sites and seasonal sites. But again, all of them were sampled 4 times a year. And we had 4 different technologies. So we have, I have some of those pictured here. We have the Aranco Advantex AX20, the Aranco Advantex RX30, Biomicrobics Microfast, and the Norweco Singulair. We had a few different specific models of Singulair, but they were all very, very similar in design. So going forward, when I explain the differences among technologies, you'll just be seeing 4 groups, so 4 different technologies. And again, these, as you can probably see pretty clearly from the pictures, do vary in their design, but they are all designed to remove nitrogen. They're all designed to have the oxic and the anoxic component. And again, they're all designed to hit that 19 milligram per liter standard. That's the goal in Rhode Island. So we had a few questions that we wanted to target. Again, I had many questions that I targeted, but I'll be focusing on sort of my 2 biggest ones tonight. So the first question we had about these systems is whether or not total nitrogen or TN concentration varies as a function of technology type and home occupancy pattern. So those were sort of the 2 big comparisons that we were looking at. So does the performance vary based on what type of system you're using? Does it vary based on how much that system is being used? When it comes to seasonal versus year-round usage, our biggest question is really for the seasonal sites, is there any sort of ramp up time to these systems? At the beginning of the summer, after withstanding months and months of non-use, all of the microbes that are living in these systems and chewing through this nitrogen, after months of not receiving any organic or nitrogen inputs, are they able to snap right back into what they're supposed to be doing when these systems start being used at the beginning of the summer? So that's something that we were very curious about. And so in addition to looking at the total nitrogen concentration, we also wanted to look at the mass nitrogen load coming from these outs. So mass load is a different way of looking at nitrogen. Concentration is what Rhode Island DEM's standard of total nitrogen refers to. So that's looking at how much nitrogen is concentrated in this effluent. However, you can also think about nitrogen from a mass loading perspective. And that's what Matt actually talked about a little bit earlier tonight. He was speaking about the physical poundage, the physical amount of nitrogen leaving these systems. And we get that information from combining the concentration, how much nitrogen are we seeing in this effluent, with the flow data from the systems. So how much flow is actually leaving these systems, how much nitrogen on the whole is actually leaving and entering the water bodies. So these are sort of 2 different ways we looked at total nitrogen, both of which give us really valuable information. All right, so I'm going to jump into my results looking at each of these questions. So you'll be seeing most of my data, all of my data in box plot form tonight. So we really like using box plots in our lab because it shows a great sort of representation of the range of the data. So here are my results looking at whether or not total nitrogen concentration varies based on technology type. So to orient you here, I have my 4 technologies on the x-axis there, right? I have AX20, Microfast, Norweco, and RX30. And I have the total nitrogen concentration that we measured from these systems on the y-axis. That red dashed line represents Rhode Island DEM's 19 milligram per liter standard. Again, all of these systems are designed to hit this threshold, but just looking at this graph, we have a few things we can take away. First of all, of course, you can see a large variation in how these systems are performing. Sometimes the technologies are hitting the threshold, they're at or below the threshold, and sometimes they're far above. So a big reason why we wanted to do this research was, despite this standard that exists, there are actually no requirements in Rhode Island to monitor these systems for effluent total nitrogen. Systems are required to be visited for, to see whether or not they need to be pumped, to check system integrity, to check the components. However, nobody is actually checking up. No one's required. These service providers are not required to check up on the nitrogen. So that was really a driving factor behind why we did this research. And as you can see, it's a good thing we did. I mean, this is just the beginning when it comes to looking at outs in Rhode Island for nitrogen, but they are not always performing as they should. Another takeaway from this graph is that really the total nitrogen does seem to vary based on your technology. So specifically, we saw that the Norweco systems produced the highest amount of total nitrogen in their systems compared to the other technologies. And, of course, in this research, our goal was never to throw any technology under the bus. We've had several meetings with representatives from these technologies and with service providers to try to figure out what's going on with the systems, make our suggestions, try to optimize performance. And so that was also a big part of more the tail end of my project, was trying to see what's going on and what can we change. Still a work in progress, but we were interested to see that despite the fact that these systems are all designed to hit the 19 milligram per liter and they're all designed to remove nitrogen, it does look like that design does influence how they're performing. Occupancy pattern was actually a different story. So here I have another box plot, but here I've grouped all of my systems together into a seasonal category represented by the blue box and a year-round category represented by the green box. And so as you can see, probably just by looking at the graph here, these boxes are very similar. So when we look at the median total nitrogen, the median is that thick line in the middle of the box. That's a good way that we use to sort of estimate in general how these systems are doing. Those median values were nearly identical for both seasonal and year-round sites. So it looks like while technology does influence total nitrogen, it does influence performance, occupancy pattern does not. And that was honestly really encouraging for us, and especially encouraging for homeowners, right? Because no matter whether you're living in these homes all year round or you're only living there in the summer, you still have to pay the same amount of money to have these systems installed, to operate them, to maintain them. So it was encouraging that even if people are only using these systems in the summer, they're still achieving nearly identical performance to systems that are used all year round. It doesn't appear that there's any major period of ramp up time for the microbes living in the systems. And it appears that they really can withstand, they're robust enough. These systems are robust enough to withstand those long periods of non-use and be able to get right back into removing the nitrogen. So that was really exciting to see. However, on the other hand, we did find that occupancy pattern specifically influences the mass load of total nitrogen. So again, I've been speaking about nitrogen concentrations, right? That's the threshold, the 19 milligram per liter standard in Rhode Island. But when we looked at mass nitrogen load, we looked at it on a daily scale and an annual scale. We found that in both situations, year-round outs produced a significantly higher mass nitrogen load than the seasonal outs. And that was partly interesting, partly unsurprising. So we expected that to be the case annually, right? Because those systems are being used all year round. They're constantly getting these inputs of wastewater. They're constantly, chewing through the organic matter and the nitrogen. They're putting out that nitrogen into the surrounding environment. Whereas seasonal homes are only doing that in the summer. So annually, we were not surprised. However, we were kind of surprised to see that the daily nitrogen load varied and that year-round systems produced more nitrogen overall than the seasonal systems. So that really tells us a few things. first of all, it appears that system usage, so how much it's used, how often it's used, does influence the physical amount of nitrogen that is being put out into the environment. And it also suggests that maybe just looking at the concentration of total nitrogen leaving these systems is not the best way to assess performance. It might be valuable to consider not only how much nitrogen is concentrated in this effluent, but how much of these systems being used, how much flow is actually leaving. And when you combine that info, how much physical nitrogen is entering the watershed. So it's just a little bit of insight into multiple ways that you can assess performance in these outs and suggest that this might be a beneficial way to assess performance and to measure nitrogen going forward. And with that, I will happily take any questions at the end. That is my email address. If you have any questions, you want to reach out to me individually. I love talking about wastewater. And also, this research was recently published in the Journal for Water, Air, and Soil Pollution, and it's actually free to read right now if you are so interested. So I want to thank you for your time and your attention, and I think I'm handing it over to Alyssa.
Thank you, Bianca. And yes, so Alyssa, whenever you're ready, you can hop on.
Unmute myself because that will help, right? I want to share my screen. Okie dokie. So, welcome everybody. I know, time's a ticking and I'm sure folks are hungry or ready to move on with their evening. So I will try not to keep you for too long because nobody likes to be held hostage by a presentation. So I'm going to change gears a little bit. So we heard from Bianca and Matt about sort of nitrogen reducing and alternative technologies and how they are protecting human health and the environment. And so I want to kind of shift our focus and talk about some of the things that I researched when I was a PhD student with Bianca in the lab of soil ecology and microbiology. And thinking about a little bit more picture, big threat, zooming out, thinking about septic systems along the southern Rhode Island coast, and thinking about how they're threatened by both rising groundwater and storm events, and just sort of kind of thinking about that from sort of a community preparedness perspective, sort of down the line so that we can be more resilient. So, I like to think of coastal septic systems, whether they be the fancy nitrogen reducing advanced systems or, plain Jane, any of the other sort of more sort of conventional systems. So they're between a rock and a hard place, right? On the one hand, they are threatened by rising groundwater tables, and on the other hand, they're threatened by coastal storms. And so first, I'm going to talk to you about rising groundwater tables, and then later on, I'll touch really briefly on some work I did about coastal storms. So, just again, Bianca already showed us this, but this is a cross section of a conventional system. So you have, all of the wastewater being produced in the house, it moves into the septic tank. And then if you don't have an advanced system, it goes straight into the drain field or soil treatment area, as Bianca called it. There's usually a little distribution box in between. And so as Matt said earlier, there's a pretty wide variety of systems out in the landscape across southern Rhode Island. This information is easy to access for the Town of Charlestown, and is much harder to kind of pin down in Westerly and South Kingstown because they don't have the same kind of database. But there are lots of systems still on the ground that were installed in the 60s, 70s, 80s, 90s, before some of the newer regulations required these advanced treatment systems that Bianca and Matt spoke about. And so if we look at a cross section of this drain field trench, here's what we see. This would be like if you sliced a loaf of bread and then looked at it on it. Okay, so there are, pipes made out of perforated PVC, and they're sort of encased in this trench or this sort of box of gravel. They call it crushed stone. And the water trickles out of the perforations in the pipe, trickles through the stone, and then it hits the bit we call the infiltrative surface. That's where the native soil begins and sort of the wastewater infrastructure that we added as humans ends. And the idea is that as the water moves through this native soil down towards the groundwater table, the soil does some work and cleans some of the contaminants out of it. Soil does a good job of removing pathogens and things that cause disease. But as Bianca and Matt indicated, they don't do a good job at reducing nitrogen. And so, as we think about upgrading, our systems along the coast, that's why it makes sense to really introduce this nitrogen removal technology. So in Rhode Island, the distance between the bottom of sort of the drain field infrastructure and the groundwater table, we call that the separation distance, and that's specified in the regulations. It has to be a minimum 4-foot distance, in the coastal area, it can be 3 feet further inland. And so one of the things that we were thinking about is that, we know that sea level rise causes groundwater to rise along the coast. And so we were wondering, these two are sort of interconnected. I have a damage here. So salt water, the ocean, actually extends inland for quite a ways below ground. And this may seem a bit of a head scratcher, but actually you've seen this. If you've ever dug a hole at the beach, not in the water, eventually if you dig down deep enough, you get to seawater, right? And so there's this diagonal wedge of salt water that underlies much of what we're standing on in the coastal area. And so if the sea level is moving up, then it's going to carry the groundwater that's fresh and is lighter and floats higher above that salt water up with it. So we were thinking, so if we have over time a raised seasonal high water table, partly as a result of, say, sea level rise, but also because we know that as climate change continues to affect our region, we are getting more intense, more frequent precipitation and sort of storm events. And over time, the precipitation patterns here in Rhode Island, except for 2020, which is right the year of outliers, period, there's a lot more precipitation happening every year. And so, over time, if our seasonal high water tables are rising, we may get into a situation where a system installed, several decades ago and had enough separation distance. Now, no longer it has enough separation distance, which means there's not enough time for the wastewater to really get cleaned by the soil. And so we wanted to know, right? Should we be anxious about this separation distance impairment? And so we looked at this from two sort of perspectives. We looked at some historic data and tried to kind of think, so what have groundwater tables done over time? And then we looked at 10 sites in the field with drain fields that were put in at some point in the past and looked at, okay, can we see this, right? Is there inadequate separation distance, like in real life, not just theoretically? And so the way we want to add collecting historical data is actually, I combed through property records and matched up past property owners with systems along the coast, within a couple of 100 feet of a shoreline, either the ocean itself or one of the salt ponds. And I found the septic system permits in the DEM database. And on the septic system permit, because part is the depth from the ground surface to the groundwater table, because this is something then they use to create the wastewater, the on-site wastewater treatment system or septic system. And so I pulled all of that information and I was able to graph it. And so this is what that looks like. So here you have time across the x-axis, right? The oldest data was from 1968. As Matt said, previous to then, nobody cared, and it was the wild, wild west of Southern Rhode Island. And then here you have 0, where I put the grass as the ground surface, and then we're looking at distance below the ground. And each dot represents a property with a depth from the ground surface down to the water table. Okay, this is in centimeters, but you can convert this to feet or yards. 100 centimeters is roughly a yard, just over. And so each dot is a measurement, and this red line is the RIDEM requirement for how deep the water table had to be at that time. And so for a while, it was 4 feet from the ground surface, or 4 feet from the ground surface. And then in sort of the late knots, it went down to 5 feet. Okay, so right now you can't have a system unless there's 5 feet of groundwater, although then you get into the advanced systems, and that is another reason that they're really popular along the coast, because you can kind of play around with your depth of groundwater. And so what else you see here is this blue line, and that's a regression. It's just the linear best fit line. And what it tells us is that over time, based on these data points, it looks like groundwater tables are rising at about 1/2 inch, 14 millimeters a year, which is a bit shocking. Because a couple of different reasons. But one thing to note is that sort of how fast water tables seem to be rising varies along the coast. There's sort of lots of caveats and complications that go into this, but some of these properties had multiple measurements over time because like a storm came and wiped out the system, or they added a bedroom and needed a new system. And so for about 50 of the properties, this represents about 380 properties, 50 properties had repeat measurements. And when you kind of look at those measurements over time, 65% of the properties that had multiple measurements definitely showed groundwater getting closer to the surface, rising over time. So this is not just an artifact of funky data. The other thing that's really interesting is that this 14 millimeters per year of rise is much faster than the 3 millimeters of sea level rise. We've documented at the Newport Tidal Station. And so that has lots of interesting sort of things to scratch our heads about. But part of what we think is that the ground, even though parts of Charlestown are, on individual wells, other parts, including parts of Charlestown, are actually importing groundwater and then recharging it with their on-site system. So for example, in Westerly, everybody's on town water, but uses an on-site system. You're piping in water from somewhere else and adding it to the groundwater. So that's going to cause it to rise over time. Parts of sort of the waterfront areas, especially on sort of beach areas in Charlestown, even though they don't have a municipal system, they have big cisterns that get filled by a big water tanker truck occasionally. And so again, you're bringing water from far away to the local area, and over time that is contributing to what the groundwater rise. Okay, so that's nice, that's theoretical, that's great. What if this is just some crazy thing some scientist came up with to sound the bells of doom and gloom? So we decided to say, okay, in real life, is this happening? And so the way we went about this is we tried to find 10 sites. And again, as Matt said, I sent out 200 some letters to folks that lived within 200 feet or so of a shoreline, had sandy soils that they lived in. And I tried to get them to volunteer for participation. And I had a much worse rate of return than Matt did. I finally got 10 people to agree to participate, and I was super grateful. And so what we did at each property where I got agreement, I had to have an on-site wastewater or a septic system plan in hand so that we could see what we were supposed to be seeing. And at each property, we put in a groundwater monitoring well. It's just a shallow a PVC pipe. It's about 2 or 3 yards long, extends below the ground, has little holes in it. And then we hang a logger inside, and that logger tells us, and it records every 5 to 10 minutes, how high or low the groundwater table is in that well over time. And so we paired that information with, and these were in place for years. So like we know, I can go back to any date and say like, okay, at 3 o'clock on Sunday the 14th, this is where the water table was. And we can kind of compare that to what the plan said. And we can also use something called ground penetrating radar, which is what this little buggy jogging stroller looking thing is. Down here is an antenna. It sends electromagnetic waves down through the soil and they bounce off, sort of changes. And then you get this weird black wobbly wave pattern. It's kind of like a sonogram, like people get in pregnancy, okay? And so when you drive this GPR across the surface of the drain field, you can very distinctly see within this red box, if you kind of fuzz your eyes and look at it sideways, there are these 4 darker blobs within, and those are actually concrete drain field structures. And so we were able to compare this information and kind of take this water table information over time and look at the property, the wastewater system, that property over time, and understand, is this distance shrinking? Is this like a real thing that we can see in real life? And so it turns out it's actually a really common problem. 20% of our systems did not have any kind of impairments of the seasonal high water table being too high, and therefore there not being enough separation distance. But half of the systems had a problem with the seasonal high water table being higher than it ought to have been in order to maintain that separation distance, at least some of them. And then 30% of the systems in my study always had a problem. They never had enough separation distance. And sort of to add insult to injury here, at some times in the if there was a big enough storm, the water actually made it up to the infiltrative surface. And that means raw wastewater is leaving the septic tank and literally just mixing with the groundwater. And that's horrifying for lots of reasons that Matt and Bianca touched on earlier. And so this idea that this impaired separation distance really is, we've documented that's a current problem, and it's going to continue to be a problem for systems as we continue to sort of grapple with sea level rise in these areas and as groundwater tables continue to change. And so that's sort of one part of the story. So now really quick before you all, mutiny on me, I'll talk really quickly about some of the things about storms that I looked into, kind of thinking about from the other threat perspective. And so kind of when I started this in like 2017-ish, there was this like thing that the Army Corps had decided they were going to raise a whole bunch of the houses along Southern Rhode Island, right? That was like a thing, right? And they were going to spend $56 million to do this. I have lots of feelings about that. But that made me wonder was like, okay, cool, you can raise the house up above the floodlight, right? So after a storm, you walk along the beach and you see stuff like this. And for those of you who are not used to looking at this, this is a galley system. So this is part of a wastewater treatment, a septic system drain field. This is an old cesspool. Right here we are at the beach. Here's the ocean. Here is another type of on-site wastewater treatment infrastructure. And so raising the house doesn't really solve the problem here, right? It saves the house, but we can't raise our below ground infrastructure. So disconnect. So anyway, so I wanted to know, okay, so maybe we can do some modeling and some predicting. And so maybe we can say if like a storm of X type hits the coast, how many systems are we looking at, right? Sort of Hurricane Sandy kind of revealed for many coastal communities just how vulnerable they are to these kinds of events, right? And so what happens in a storm here, I have a little graphic, right? We have our storm coming in and it raises, right? We get storm surge and we get the waves. And, you know, over time, we have this like massive, the peak of the storm, and then eventually kind of the storm recedes and then everything's fine. And so what we thought about was that the systems, the properties here on the different areas of the landscape may or may not be at different risk levels for damage to their systems based on how long they were flooded for and how fast that water was moving, maybe across them and maybe scoured away some of the things. Those pictures that I showed from the beach, clearly that was fast moving water that washed away the sand and left the concrete stuff behind, right? But if something's flooded for a long time and there's any kind of air in there, you know, sandy soils, you know, clams can wiggle and shoot down through the soil, right? It kind of fluidizes. So could that happen to wastewater infrastructure? Jury's out on that. But, you know, chances are the systems that are right on the beach or sort of really in the low-lying areas around the pond are going to be more seriously affected by this kind of storm event than systems that are higher up in the landscape and further inland. And so, you know, systems might experience ephemeral problems or afterwards might have moderate or serious damage. And that's sort of kind of how we did this. And basically we used some existing flood maps and we used GIS the way Matt mentioned earlier. And sort of the short version of the story is that depending on the type of storm that hits, a different number of systems are affected. So there's some weird terminology that people use to describe storms, and it's a 25-year storm or a 100-year storm or a 500-year storm, right? So Hurricane Sandy is anywhere 100-year to 1,000-year, and what that means is that there is a 1 in 100 or 1 in 1,000 chance any given year of that storm hitting. So if you're in the 100-year floodplain, it doesn't mean you're only going to be flooded once in 100 years. It means that any year you have a 1 in 100 chance of getting flooded, which means you could have 2 years in a row where a 100-year storm comes. Unlikely. Could happen though. You never know, right? And so, you know, a 25-year storm is going to be a smaller storm because it's got a greater chance of happening than say a 500. And so overall, 3,000 to 4,000 systems will experience some level of flooding during the course of any of these kind of events. And if you're looking at hurricanes and sort of worst case flooding from there, right, anywhere from a category 1 to category 4, you're looking at 2,000 to 5,000 systems. So from a flooding perspective, best case scenario, a category 1 hurricane hit us, but that's from below ground, right? We'd be in much bigger trouble if it actually hit. And we know that a category 4 hurricane is probably pretty unlikely to hit Rhode Island, but you never know. So, you know, that's why there's that question mark, because, you know, that number is tricky to predict. And so regardless, overall, after the fact, there are going to be about 200 systems, plus or minus, depending on how you kind of tweak the model parameters, that are going to be seriously affected and probably toast. So these are 200 systems that are going to need to be repaired or replaced completely. And then there is another 65 to a couple hundred that are going to be moderately affected, but like some professionals are going to need to go out and inspect it and make a determination. And the rest will probably just be flooded for a little while. And then once the floodwaters go away, everything's fine. That's not a big deal. And so, you know, if we add sea level rise, you know, the flooding creeps a little bit higher and we have more systems that will be temporarily flooded, but probably will be fine in the long run. But one thing, you know, is to think about, so we need professionals to go out and make repairs to this many systems. And like, do we have that kind of capacity? How long would that take? You know, thinking kind of through this and understanding sort of what as a community do we need to do in the aftermath of a storm like this? Do people know what to do? Is something maybe perhaps would be worth considering and thinking about. Another thing that we know from post-Sandy is that all of our advanced nitrogen removal treatment systems, if they are not properly designed to withstand storm events, they are actually at much greater risk and much more likely to be damaged and like damaged things missing that got ripped and floated away than some of the more conventional concrete underground structures that are less affected by that kind of thing. So that's another important consideration, thinking about how can we design the systems we're putting in the ground now to make sure that they are not washed away by the next storm. So, you know, why this is concerning? these repairs and replacements that are going to need to happen are going to take time, like weeks to months, right? Best case scenario. And then who gets to go first and who goes last? It's going to be expensive. Someone's got to pay for it, right? And FEMA money sometimes takes a while to come through. So who's going to pay for it in the meantime, right? And those repairs could run $1,000, $15,000, a new system altogether, and Matt has some different numbers for that you mentioned earlier. Ballpark, this is what the DEM says to budget. And so meanwhile, what's happening to the wastewater? Right? I mean, sometimes if the house is damaged, people won't live there, but there's going to be ones that, people can live in that house. Will they know not to use the water? Will they know not to drink the water? Will they know not to go swimming nearby? And so these are all things that I think over time, or like soon rather, we should think about before the next storm. And so to kind of just sum up, again, coastal systems are being threatened by both rising groundwater tables and coastal storms. And this can lead to failing or failed septic systems. And that is a problem from a nutrient and pathogen pollution perspective, the way as Bianca and Matt mentioned earlier. So that can contaminate coastal waters, and it can also contaminate drinking water wells. And so that can lead to sort of environmental health problems that Bianca mentioned, or algal blooms, fish kills, shellfish closures and die-offs, and human health problems, because if we drink a bunch of contaminated water, that's not good for us. And so that's the end of the story here. With that, I'd like to thank some of the dream team that did some of the ground penetrating radar work with us. And my collaborators, and I will hopefully there's time for questions.
So thank you, Alyssa, for that. So I will stay on the line for questions. I know that we've been on here for a little over an hour now, but if you have any questions and you can't stay on, feel free to email me them at saltpondscoalition@gmail.com, and I can get them to either Matt, Bianca, or Alyssa. If you have any questions, I can't see everybody on my screen at once, but you can raise your hand or just type that you have a question in the chat, and I can either read the question out loud or call on you to unmute yourself and ask your question. So first, I just want to thank Matt, Bianca, and Alyssa. And we do have a question from Phil Mareshi for Matt. One question he had about what you were speaking of, are the wells on the properties that you were talking about constructed to contemporary health standards?
Okay, so that was part of the 240 wells that we got nitrogen data from. We don't really know what the well construction is for those wells. However, we make an assumption that probably the majority of those wells are, because they're located within the coastal zone. Any deep drilled wells within the coastal zone are potentially going to intercept that saltwater wedge that Alyssa was talking about. So the assumption is that the majority of the wells are likely to be point-driven wells, shallow dug wells, or point-driven wells. Does that answer your question?
Perfect. Bianca, a question for you, also from Phil. Is there any modification to behavior that could affect a system's operation? Kind of if it's yellow, let it mellow type approach, or other water conservation measures that could help with nutrient loading in these systems?
That's a really good question. I think that when it comes to sort of mitigating these threats, I think that educating the homeowner is a huge area of potential. I mean, so many of the people who were part of this study that we met with and just happened to chat with in the field were like really excited and were really open to learning about what we were doing. And myself being a first-time homeowner, if I weren't studying wastewater treatment, I wouldn't know anything about my septic system, and I think that explaining about water conservation, explaining about sort of evening out how you are using your system. And I think explaining like why that matters to the homeowner, maybe talking a little bit about the nitrogen problem and why we should care about how much nitrogen loaded water is leaving the systems definitely has a benefit or has the potential to help with this problem. I think that can be achieved through outreach or even through like a pamphlet or an email blast from septic service providers or the technology people. I think there are so many opportunities for advancement when it comes to that. And I think that is a really good step in the direction that we're trying to achieve here with maximizing this performance. So yeah, I definitely agree. That's a really good point.
Thank you, Bianca. Matt, I think this is another question for you from Raymond Martino. Should we expect a mandate to upgrade to nitrogen removal systems in the future?
On top of the existing one, DEM does require that any septic system that's being replaced within the critical resource area, which is the Salt Ponds region, to be upgraded or to utilize nitrogen reducing technology. And that goes for new building construction on a vacant lot or any addition that's being done to an older dwelling that has a septic system that's was installed before 2002. There's a likely chance that septic system would already have to be upgraded to nitrogen reducing technology. As far as a mandate goes, I know we're not really looking at implementing any sort of regulation or draconian rules or anything like that. What I would like to do is try and seek out funding to do more projects like the one we just completed with the 15 septic system upgrades. If we can tap into this grant funding, EPA grant funding. EPA has this SNEP program is a great program. Our project was highly well received by my grant coordinator at the EPA. They did indicate to me that we ought to keep trying to get some additional funding, and given the success of our project as a whole, we're going to be looked favorably upon for forthcoming grant applications. So as far as a mandate goes, no, but additional funding, yes.
Thank you, Matt. I have two more questions in the chat. The first one is for Alyssa from Russ O'Haver. How does the impact of sea level rise impact marsh grass health, given that marsh grass is often a nitrogen sink?
So that's a good question, right? Marshes and grasses and sort of accretion and all that is sort of a complex thing. And I know some other folks who work a lot in marshes and have been looking at that. So I can pass you on to them and they may be able to answer this a little bit more broadly. But any vegetation is a nitrogen sink, right? So is the grass on your lawn, which is, a whole nother story. If marshes can keep up with sea level rise, then fine, but they can't always, right? And if we've constrained them by all kinds of artificial construction in our nearshore areas, then they may or may not be able to keep up with sea level rise, which means, if our marshes don't make it, we're sort of at a much increased risk for flooding and those kinds of things, right? Because marshes do a lot of important work for that. But yeah, you're right. It also has sort of implications for any kind of nitrogen that's in the system that could potentially maybe be scavenged by these plants and dealt with. I don't know. I don't really have a good answer for that. But if you are interested, I can connect you with some folks who might be able to answer it a little bit more specifically.
Thank you. And the last question is from Bob Pompey, and I think, Matt, this will be for you again. Is there anything, or Bianca perhaps, is there anything in the works to measure the output performance or efficiency of OWTS systems?
I can start with this one, and maybe Bianca can pick up a little bit. But the state of Rhode Island, like Bianca mentioned, doesn't have a requirement for effluent quality sampling for nitrogen reducing septic systems. However, another study that Bianca did was identify a low cost field screening method or initial screening method that can be done to gauge the efficiency of nitrogen reduction from effluent from these systems. And based on her findings, that is really the main reason why I asked the 15 homeowners where the septic systems were upgraded to grant us access to their property for up to 5 years after the system was installed to implement the method that Bianca had identified for screening nitrogen concentrations. I don't know if Bianca, you want to touch on that a little bit?
Yeah, absolutely. So this was a whole nother chapter of my dissertation, and it's called a photometer. So it's essentially a benchtop product about this big, and it can be used to measure effluent ammonium concentrations and effluent nitrate concentrations. And we did a bunch of sort of accuracy assessments to see whether or not it's actually good at assessing those values and whether or not it can be used in the lab and in the field. So we found that the answer was yes to both, which was really exciting. So we found you can use the photometer to essentially, if you want to do the analyses in the field, just bring it out, bring some sort of power source and test the effluent in the field. Now, I say it looks at ammonium and nitrate. It's not capable of measuring total nitrogen itself, but total nitrogen simply means the sum of ammonium, nitrate, and organic nitrogen in wastewater. And in these advanced end removal outs, organic nitrogen is typically very, very low. So we felt that it was a safe bet that if you measured the ammonium and nitrate and added that together, you could approximate the total nitrogen. So as I said, we did a bunch of accuracy assessments to see whether or not that was true. And not only can it accurately measure ammonium and nitrate, it can consistently estimate total nitrogen, right? So it's not going to give you the perfect value. It's not going to give you the perfect number for total nitrogen, but it's going to be sort of a approximation that you can use to triage, especially systems that might be teetering on the line of that 19 milligram per liter threshold. So we were really excited about that. It takes about maybe 20 minutes to do the whole setup and analysis and breakdown with this photometer. We did a cost benefit analysis as well to compare the cost of running samples yourself on the photometer versus sending samples out to like an environmental testing lab. So we compared those costs to several environmental testing labs in Rhode Island. And we found that while the photometer has a higher like upfront cost, you have to buy the photometer itself, which baseline photometers cost about $500, give or take. But after between 10 and 30 samples, depending on what you were looking at, it became more cost efficient to run the samples yourself. So it was really exciting because it seems like a very viable and accessible and user-friendly way to get out there and see if these systems are performing like they should. So we were really excited to see that.
So with the 15 systems that were installed under the grant, I have an intern at the town, and he and I have been going out monthly to collect samples to run for the photometer. And it's like Bianca said, it's a good way to triage systems. You could also use those data if there's a recirculation ratio in the system and you have a high detection of nitrogen, you can mitigate the nitrogen reduction by augmenting the recirculation ratio if necessary. You could have a conversation with the property owner to figure out what's going on in the dwelling. So it gives us an opportunity to engage with the homeowner and engage with the system to try and optimize functionality.
Plus, like a standard lab result, you're going to wait, maybe a week to get the answers. With a photometer, you have instant gratification, basically, 20 minutes.
Yeah, exactly.
I'm going to leave it at one last question, and then I think we'll end. From Charles Grief, has any groundwater monitoring for nitrogen been done adjacent to existing systems, or is just well water sampled?
So my project specifically did not include groundwater monitoring because I figured that was going to be a pretty much like a the opposite of an incentive to participate. So I don't think people wanted to know and wanted to be implicated in that. And I can turn the rest over to what was actually sent to Matt.
So the analysis that the town did, looking at nitrogen concentrations in shallow groundwater, that was all done using potable wells. Years ago, we did install some test wells on some town-owned property to try and understand what was happening with some outwelling of nutrient-laden groundwater. That was a very small scale study. It was done in one small lot. So that's really it. The bulk of our knowledge of groundwater nitrogen concentrations originates from those 239 private wells.
One last question, just because this is really good and it's been asked now. There's two questions that kind of go along, one from Scott Warneroff, one from Ray Seeplick. The first just being, given the challenge outlined tonight, how do you view potable water availability or security in the Rhode Island coastal area going forward? The talk about prevention was informative, but what extent are new supplies of fresh water being evaluated? And then adding on to that, given that septic systems are under siege, our potable water is a great issue. What is being done by the town to secure a water source for areas along the coast? In other words, would it help to get a community water system?
I think there have been some discussions to that end. I think the town council, this previous town council, was involved with some discussions. I think Bob Pompey was actually part of those discussions, and the CLEBA and the Central Beach Water Associations. Honestly, I don't know where this goes from here. And these are higher level discussions that are required to be held, typically on a town council level. What I can do and what I do for the town council and the town administrator and boards and commissions is I can provide data, and I can provide some expertise relative to septic systems, and we can lean on our experts also for some expertise. But that's what I can do is advise, and I can leave the rest to the town council and town administrator.
I could add on to that. So one thing to think about, right? This is not my own drinking water, right? I live elsewhere, so I don't have to worry about this. So, from a distant perspective, if folks are no longer drinking the water beneath their feet, are they really going to care about it? So one thing, if you're decoupling folks from the groundwater in their own property, the motivation to make sure that their system is functioning, their septic system is functioning well, now is not as, I would say, pressing, right? And so, but the effects of then continuing to contaminate the groundwater is going to eventually rear its ugly head in a huge environmental catastrophe, which is going to be like impossible to deal with, right? Once the entire Ninigret pond becomes eutrophied, there's no going back. And so that is one of the risks if we focus on no longer drinking coastal water resources, because they have lots of issues, right? I didn't even talk about saltwater intrusion, and that's something that Jeevan, who's on here today, could talk about. That's something he researches. I saw him in the audience. He's a grad student at URI looking at saltwater intrusion in southern Rhode Island. And so, there's lots of things happening, but one of the things that I think is worth sort of discussing is thinking about what are people's motivation in protecting their coastal groundwater resources. And by not drinking it, the immediate reason to care, I think, is removed a little bit. And I think that's dangerous. And I will leave it at that.
I agree. And, again, the conversations that I personally have had with people in the field when we've been sampling, when I have noticed, and I'm sure this obviously isn't the case with everybody, but I have noticed that when people are learning about, as Alyssa said, what's going on under their feet, I saw some immediate light bulb moments and a senses of sort of accountability. They were excited to see, oh, hey, how's my system doing? Like, what does this mean? And, what's my system report card? And so I think that a sense of ownership sort of in this issue, like Alyssa said, is really important. And I think that's just another reason and why we should really advocate for educating homeowners so that they understand like why we care about this issue and why what they put into their systems actually matters, not just for them, but just sort of for everybody in the environment as a whole. So yeah, I agree. I think that it's a difficult conversation because it's sort of forcing people to look at way down the road effects and really have to take a good hard look at themselves and what's going to make them care. But I have definitely seen that a sense of accountability, I think it improves people's understandings and why they care about this issue.
Thank you, guys. So since we're just at just about at 8 o'clock, I think I'm gonna let everybody go. If you have any other questions that you want me to direct, like I said, just email me at saltpondscoalition@gmail.com. And if I just want to thank once again Matt, Alyssa, and Bianca for being here tonight, and thank all of you for coming. So have a great night, everybody.